All right. Maybe during the break I managed to open it again, and can you see the slides? Okay. So today we want to talk about the ISA, and last time I show you this picture where we talked about different eras in our design of computer systems and computer architecture. We start with talking about the fact that we have better systems and better device technology. Then we talked about this area here, which was the golden age of computer architecture in the middle. And then we talked about these other three areas, which we said that this is basically what we are facing now because of the Powerwall, because of the Amdahl's law, and so on and so forth. All right. Moving forward, the question, of course, is where are we heading, and is this it? Is this the end of our quest to make the computer faster and faster? And should we expect that from now on the computer is going to be having the same performance? And the answer to that is no. There are lots of other things that we are doing right now, and part of active research of people in the computer architecture domain. The three main things is what's called a more than more, and what's called a beyond CMOS. I decided to move this second part of the discussion to the end of class in week 10 when we are actually reviewing stuff. So I'm not going to describe these three for now. I'm going to describe it later in the later part of the lecture. Part of the quarter. Okay. But just a quick takeaways of things that we discussed so far. So we historically managed to double the performance every 2 years almost. This is the prediction that Gordon Moore's had, and we managed to actually satisfy that requirement. We also use lots of microarchitectural tricks in order to make the system faster and faster. And that's, if you remember, it was like more than 20x order of 20x better performance. And that's mainly the things that we're going to discuss mainly at the first half of the class. Then we hit the Powerwall, and then we move to the multi-core era, which we're also going to discuss in this class. And there are new technologies and methods that we will using right now and in future in order to continue this trend of improving the performance, which later on in the course I'm gonna talk about. Okay. Any questions about the things that we discussed last week about the general trend, about the Moore's law or anything like that? Cool. So now let's actually move on to the second, the main thing that we want to talk about in this lecture, and that's the instruction set architecture. I briefly talk about why we need instruction set architecture. So remember, I show you this picture, and I told you that we have different languages, different apps in different languages, and we also have different different hardware. Each company, each vendor has its own hardware, it has its own proprietary information, and so on. And there's this system software in between these two that needs to somehow manage this compatibility issue, right? And in order to maintain this compatibility, in order to provide this service for every single app and every single hardware vendor, we said that everybody should follow this specific contract between the software and the hardware, and where the software and hardware agrees that they support this list of instructions. So we define what instruction is, and that would be the main part of this lecture. And once we understand what these instructions are, then everybody agrees that if they are following that specific ISA standard, then they will have those lists of instruction. The software will translate into the list of instruction, and the hardware will take that list of instruction as the input and start executing those instructions. So this is the basics of the instruction set architecture, or the ISA. To give you a little bit more background, as I said, the ISA is the contract between the hardware and software. Basically, what would be visible to the software, as I described last time, is memory addresses, registers, which we're going to talk about, and some semantics of that instruction, the order of instructions, and the relationship between the instructions. Historically, IBM 360 machine was like first line of work that's kind of like create this ISA form of implementation. But one thing that to pay a lot of attention to, which we actually our discussion next week, is that one ISA can also be implemented multiple different times. So the actual underlying hardware is completely independent of what the ISA is. You can use, for example, x86 ISA, which Intel is using, but also AMD is using. All of them are using x86 or what's called AMD 64 ISA, but they have very, very different implementation of this exact same ISA. Also, within the same vendor, there are multiple different. So, for example, from one generation of Intel processor to another generation of Intel processor, they still do the same ISA, but with different implementation. And next, we're going to actually talk about implementing the ISA in hardware, and you will see what do I mean by different implementation. Okay. And the same story for ARM. ARM is widely used at the mobile device layer, and you will see that, for example, Apple is technically using ARM ISA. I mean, it used to. Now they have their own. Samsung, Qualcomm, and all those different companies. In this class, as I said, we're going to use RISC-V ISA. And the reason that we're going to use RISC-V, I'm gonna get into the next slide. But generally, have this idea that our design methodology is that typically ISAs are coupled with a macro architectural style in mind. So, for example, the one that we're going to talk about is what's called a RISC ISA, which is generally what is called as a hardwire and pipeline ISA. I'm going to briefly talk about all these other methods like a CISC or VLIW or Java virtual machines, but generally have the idea that when we use a specific ISA, we also have a specific type of implementation in mind. In this course, we're going to focus on pipeline designs because that's the most widely used type of macro architecture that we're going to have. But keep in mind that there are others, including microcode, which, like, Intel is specifically using a lot. If we have time, we're going to discuss those things. But our main focus, as I'm kind of like highlighting at the end of here, is we're going to talk about a RISC-based ISA, which is a hardwire and pipeline. And I'm going to discuss that in the next few lectures. All right. So now that we kind of know what's going on with the ISA, there are different standards, there are different technologies. We're gonna specifically focus on one, and for the rest of this lecture, we're gonna talk about this specific one. So what is RISC-V? So RISC-V is written as RISC-V, but the V is actually pronounced 5, number 5. It's an open source ISA. By open source, it means that if you build hardware based on this ISA, you don't need to pay royalty to the company that create this. So, for example, if you're a company like Apple or Qualcomm and you want to use ARM ISA is proprietary, which means that anybody who builds a hardware base of that, they have to pay a royalty fee to ARM. Versus RISC-V is basically open source, so whoever wants to use it, they are free to use it. There's no IP associated with it. It came off of universities, actually came off UC Berkeley in 2010, like around 15 years ago. And the reason that it's been called RISC-V is kind of like the fifth attempt to creating something like this, which eventually worked. So that's the reason that they call it 5. Nowadays, it's very, very popular and mainly maintained by open source community. Think about it as something equivalent to Linux for operating systems. And there are a bunch of different implementation and standards within the RISC-V itself. What we're going to focus on is the 32 base version. So we usually write it as RV32i. So I'm going to talk about what are the differences, but for now, just keep in mind that we're going to use the 32-bit version because there's a 16 version and there's 64 version. We're going to focus on the 32-bit version, and we're going to start with the base set of instructions, those that commonly will be used in every computer that we're going to have that is based off RISC-V. Okay? Any questions so far? So all of these terminologies I'm going to expand and explain to you. So if you still not sure what is RISC, what is CISC, what is base, why we have difference between 32 and 64, as I'm describing things, it makes more sense to you. Okay? So what is RISC? As I said, this is a RISC-based RSA. RISC stands for Reduced Instruction Set Computers. The alternative to RISC is CISC, which is complex instruction set computers. The difference between these two is RISC-based ISAs are simpler because they have fixed size. So every instruction, as I said, is a specific number of bits. So for example, given that we are focusing on 32 bits RISC-V, every instruction that we're going to deal with is going to be 32 bits long. Okay, so if you want to store it in the memory, we need 32 bits of memory to store it. All right, versus CISC is actually it's a complex set instruction, which means that some of the instruction might takes 2 bytes, some of them might be 3 bytes, some of them might be 4 bytes, and so on and so forth. There's a specific reason for that, which I'm not going to get into. But what we're going to care about is that every instruction that we're going to see is the exact same size. And the good thing about this is that it makes our operations very simple, because we always know that we're going to read 4 bytes, which is going to be the 32 bits that we are talking about. And we're going to decode this to understand what instruction this is. And then we're going to do something about it. Versus the CISC one, decoding is very complex because depending on the first 2 bytes, we need to maybe fetch more or less and make some decisions. So it's kind of like everything is kind of on the fly. We need to make dynamic decisions. But in some cases, that leads to better efficiency. But again, we're going to focus on RISC, which is everything is fixed size, and we don't need to be worried about variability and complexity and so on. OK? Any question about RISC or CISC? If you want to learn more, follow this webpage, which is part of the a course for Stanford, a computer architecture course for Stanford. They actually very nicely give you a little bit more background on what is the difference between CISC and RISC and some examples. Especially after this lecture, once you know how the instructions in RISC-V look like, you will understand it better that what's the difference between RISC and CISC. OK? So the reason that we chose RISC versus CISC is that RISC is actually the ones that have been widely used. So everything except x86 or AMD 65 is actually RISC. So the MIPS, the ARM ISA, PowerPC ISA, and of course RISC-V ISA, all of them are RISC-based ISAs. And generally, there is this interest in moving toward using RISC. The reason that Intel is not using RISC and using CISC mainly because of backward compatibility, and the complexity of the design is so high that it doesn't worth to switch to a RISC system. It's kind of like quarter system versus semester system. Everybody knows like the semester system is better, but it's just too hard to switch. So it's kind of like this. It's kind of the same strategy that is happening right now for RISC versus CISC. So that's why we understand RISC. And then another thing is that understanding RISC is much more simpler because, as I said, everything is like kind of like predefined and easy to understand. So that's why we are focusing on RISC. All right. So now that we kind of like have this background, now let's actually go deep into designing a RISC-V ISA. If you are a designer, what are the things that we need to consider? What are the steps in creating an instruction? What is an instruction anyway? And what are the different options? These are the things that we're going to talk about. So the first step is we will have a piece of software in some high-level language like C or Python and so on. And we want to create this into what's called an assembly language, which is basically lists of instructions that we are talking about, right? And we're not going to discuss yet about from this assembly instruction, how to translate it into hardware language, which is basically, as I said before in the previous lecture, it's going to be list of zeros and ones. So we call that the machine code. So for now, we are focusing on what's called an assembly code, which we want to generate a list of instructions with some operands. We also want, for now, talk about how we actually upload this into hardware and how the hardware will execute this. That's a discussion for the next lecture that we're going to talk about. For now, we're going to just focus on how to create this list of instructions and what are these instructions and why we are choosing these instructions. OK? All right. So instructions typically actually both RISC and CISC, and regardless of whether it's a RISC-V or MIPS or ARM, they typically look like this. So there is like a command part, usually on the left, and there are a bunch of operands. It could be 1 operand, 2 operands, 3 operands, depending on different ISAs. You might have multiple different operands. As I said, we are focusing on RISC-V for 32-bit version. So every instruction that we are dealing with going to have 32 bits of value. All right. So let's focus on the operand part first, and then we're going to move on to the command part. And once we all understand both of these part of the puzzle, then we understand how the instructions will look like. Okay. So operands in RISC-V, and this is actually general again for the other RISC-based ISAs, is that there are 3 types of operands we usually use. There are registers, there are immediates, and there are memories. I'm going to go through each of these one by one to give you an overview of what are these. So let's first start with registers. So what is a register? Register is actually a hardware concept. So it has a literal implementation in hardware. Think about it as an array that we implement inside the hardware. And usually different architectures have different number of registers, typically in order of 32 or 64 and so on and so forth. Okay. The reason that we have registers is registers are this small part of they are kind of a memory, but they are much more faster than memory. Later on in the course, when we are actually talking about memory and memory hierarchy, you will see that why registers are much more faster than memory, and why we cannot just only deal with registers. But for now, just think about registers as this piece of hardware inside the processor that's kind of like acts like a very small array that we can write things and read things from it very quickly. So within one cycle, like same speed as adding 2 numbers together, you can read numbers from a register. All right. So as I said, these things that I just said, registers are much more faster than memory, but generally very smaller. And one thing that you will see a lot in this course is that generally things that are smaller are much more faster. And if you want area and you want size, unfortunately, you have to sacrifice the speed, the performance. And another big thing about the registers is that they can be seen by software. And for now, just assume that we can do it. There's one tiny detail that I'll describe it later in the course. But for now, know that generally when you're writing your assembly code, you can actually know how many registers this hardware has. Although it's a hardware concept, as I said, it can be accessed through the instructions and through the software. All right. And as I said, typically there is like 16 to 64 number of registers that we use in the ISA. The reason that we're not going beyond 64 is typically because of the performance reasons, because it takes a lot of area, the size of the instruction gets bigger and bigger, and all those problems that I'm going to get into actually. But for now, just keep in mind that we have somewhere between 16 to 64 registers in these modern ISAs, and that's actually turns out to be enough. Another big question about the register is what should be the size of the register. So we have, for example, 32 of these registers, but should these registers be, for example, 1 byte, should be 2 bytes, they should be like 8 bytes? What is the width of the registers? And the answer to that is basically a trade-off between power and area versus the performance. Of course, bigger registers means things are faster, but bigger register means that also we'll spend a lot of power and spend a lot of area in the system. Okay, so that's why this number that I talked about, this 32, 64, 16, is the size of the instruction is also usually referred to the size of the register. So if you have a 32-bit instruction size, we typically follow the same format for the registers as well. So registers are also 32. So when we are saying that we are focusing on RISC-V, the 32 version, it means that all of our individual registers each one are 32-bit. Okay, but there is also 64-bit version, which means that everything would be 64-bit. And this actually translates into your system as well. So you probably have heard that your system is 64-bit versus your system, like Windows system, is 32-bit. In the past, most of the systems have been 32 bits, but given that we managed to, pack more transistors in the system, we moved to 64-bit version. So like all of your operating system these days are by default are 64-bit version, which means that your individual register size are 64-bit. Okay. As I said, it means more power, more performance, more area, but on the other hand, it means better performance. So a 64 version of Windows is much more faster than the 32 version of Windows. And again, once we actually talk about the commands, because right now we are just talking about the operands, but once I talk about the commands, you will understand why 64-bit is better than 32 bits. But you probably can guess, because for example, if you add two numbers, let's say you want to add two arrays together, if you have more register, like bigger size for your registers, it means that you can add these two numbers much more faster, right? So that's kind of like the very basic reason that what we have registers. Any questions so far? Yes. So the question is, I mentioned that registers are much more faster than accessing the main memory. Yes. And but I also said that generally having more register means more power, and that's the thing that we try to avoid. Once I get to the design of the memory and the design of the register at the hardware level, you will understand the difference between these two, and you will see why registers are more power hungry. To give you a basic idea, think about that. In order to implement a register, we need somewhere between 6 to 8 transistors, versus for accessing 1 bit of memory, you just need 1 transistor. So you have 8 transistor versus 1, and that 8 transistor, think about it as 8 people helping each other in order to give you something versus 1 person helping you. And that 8 person can give you much more faster answer, but at the same time they occupy more area, and they also occupy more power, because 8 of them versus 1 of them, of course, is bigger. So that's kind of like the basic reason. We're going to get into the actual details of the circuit. I got a question here, and then there. The register width has any relation to the instruction width? That's the question. Yes. So as I said, typically the rule of thumb is if your instructions are 32-bit or whatever bit, you follow the same for the registers, because you typically everything you do is at instruction level, so it doesn't really make sense to make it bigger. But there are instructions, there are ISAs that use smaller register size versus the instruction. That make it more efficient in terms of power, but make it much more less fast, so make it slower generally. So that's kind of like a trade-off. So for example, for embedded systems and IoTs, you go to the 16 or even 8-bit version of your registers. But for laptops or iPads or tablets and things like that, you try to maximize your register size. Question there? Can you elaborate one more time? Like what's? Mm-hmm. Mm-hmm. So the question is, what's the relationship between number of transistors and register, and what's the difference between those two? As I said, I'm gonna give you a little bit background on the circuit level side of how we actually build a register. You don't need to know it in this course. You just have to abstract away a register, and so you just say, oh, for me, register is a block that store things in 32-bit. But I'm going to give you a little bit background on how we actually build it. But again, to give you a quick overview, the idea is that in order to build a register, you need a bunch of transistors in some format and shape. And usually it takes like somewhere between 6 to 8 of those transistors in order to create 1 bit of register. But versus the memory is typically you just need one transistor. Again, why we need those things, I need to actually give you the exact circuit. But for now, just keep in mind that it's just more expensive to build a register. But on the other hand, it's much more faster. The other question.
Like if a processor has a certain number of registers, does an ISA use all of them, or like if you use a different ISA, it would use a different number of registers?
So the question is, if a processor has certain number of registers, does the ISA use all of them? And what happens if we use another ISA, right? That's the question. That's a great question. For now, just assume that hardware has the exact same number of registers as the ISA set, part of the standard. Later on, we're going to see that that's not the case. And that was the, when I said seen by software, that's what I meant. In reality, the hardware might have more than what's the ISA assume. And there's one nice trick that we can use in order to kind of like bridge between these two. But for now, to keep things simple and don't confuse you, think about the hardware has exactly the same number of registers that we think the ISA has. So for RISC-V, for example, we're going to assume that we have 32-bit wide registers, and we're actually going to have 32 registers of those. So 32 registers, and each one are 32-bit wide. Okay. And one thing to note is that we usually use this terminology of word. So when we say one word, we mean 32-bit. All right. So one word is 32-bit. Half word means half of 32 bits, which is a 16 bits. All right. So if you heard the word 32, a word, what does it mean in this class? It means it's 32 bits long. Okay. And there is an alternative for the 32-bit version, which we use as RV RISC-V32, and the alternative version is RISC-V64, which is also very popular and very widely used. The difference between these two is that instructions are 64-bit wide, and the size of the registers are also 64-bit. All right, and we usually call that double word. So the difference between RV32 and RV64 is that the register size, the width is bigger. It means that it's faster, but it's also much more power hungry. All right. And as I said, we're going to focus on the 32 version for now. We actually, so the question is like, what is the, like how many bits for shorts and doubles and all those things? I have a table later on this lecture that I list all of them. For now, just keep in mind that word means 32, double word means 64, and half word means 60. Okay? All right, so the way that we're going to show registers in RISC-V is we're going to show it with X and the number. So for example, register number 0. So it starts, first of all, it starts from 0 to 31. And for each one, we do the X plus that number. So X0, X1, X2, X3, X4. In order to kind of like, think about this as a data structure at the software level, think about it as X is the name of your array. And each of these registers is basically one line of that array. So we have a 32 element array, and we can access it from 0 all the way to 31. Okay. One important thing to remember is X0 is actually hardwired to 0. So it's actually hardwired literally by hardware to ground. So you cannot write into X0. And if you even write to X0, nothing happens because X0, think about it as a constant that is always equal to 0. You might wonder, why are we wasting one of our registers to 0? The reason is creating 0 in hardware is not a trivial task. You actually need a proper 0, and then everything it will be based on that. So if you want to initialize things in hardware to 0, it means that you actually assign it to X0. Okay, so X0 is always constant and it's always equal to 0. And if you even like add two numbers and save the value to X0, nothing will happen to X0. X0 is always stay equal to 0. Okay. Any questions? And this data structure that holds all of these registers is called register file. Okay, so when we are saying register file, is the actual hardware implementation of this register bank that has 34 of them, and each one is 32-bit. Yes, so RV32 X0 is included in that one. So you basically have 31 registers that you can assign values to it, and then one register that is always hardwired to 0. x31. Yeah, from x0 to x31. Any other questions? Cool. All right, so that's it with the registers. So as I said, registers are this data structure that we're going to use in order to hold our temporary values. It's very fast to read and write from. And there are 34 of them that we can use when we are writing our instructions. Okay. So now let's move on to the second one, which is the immediates. All right. So what is the immediates? Immediates are actually these constant numbers. They're not variables. They're actually constant numbers. So I'm actually showing you an example here. This is one instruction that we use in RISC-V. This add-I part is basically the command, which I'm going to get to soon. But these three things on the right, they're actually the operands. So as you can see, what I'm doing is I'm going to describe it later when I'm describing the commands. But what this does is adding x1 to 5 and save the results into x2. Okay, and we already know what x1 and x2 are, right? These are our registers. So the number 5 here is the immediate that we are talking about. Okay, this is the actual constant number that we are allowed to use when we are writing our instructions. Okay, it's totally fine to write any number that you want. And the nice thing about immediates that they can be also signed. So you can do -5 here as well. So if you want to do x1 -5, you can add x1 with -5, and that's the same thing. Okay. One is big thing that usually create lots of confusion is that for reasons that I'm going to explain later, the immediates are not always 32 bits. So remember, registers are always 32 bits, but immediates are not 32 bits. Usually they are 12 bits or 20 bits. There are reasons for that I'm going to get to later. But for now, just know that immediates are not technically always 32 bits. So now that we have this problem, the question is that if I want to add x1 to 5, I have this kind of segmentation problem where x1 is a 32-bit number and 5 is not necessarily a 32-bit number. It's, for example, a 12-bit number. What should we do in this case? Any suggestion? Yeah. So, but what if, so the answer was like fill the left side with zeros. But what if it's like -5? Do you also do 0 extend, or should you do something else? Yes. So what we need to do is basically we need to do sign extension. Okay. You might be worried that what is sign extension? You have no idea about sign extension. But it's nothing to be worried about. You can just very quickly after this class go and read it. It's something that you probably have learned in your CS33 or M51 course. But if you don't remember what was sign extension, my suggestion is go and quickly take a look at your notes for the past course, or the TAs will give you some basics. But generally, to give you some background, sign extension means that if you have numbers, for example, a 12-bit number, that you want to extend this 12-bit number to a 32-bit number so that you don't have the segmentation problem of like adding 2 bits together, you need to extend this value. There are 2 options that you can use in order to extend a value. You can just add zeros to it, and you add zeros on the left side because adding zeros to the left side doesn't mean anything, right? So if you have a 12-bit number and add zeros on the left side, nothing happens in terms of value to that number. But the problem is that if you remember ages ago when you took the CS33 course, there was this notion of 2's complement and the sign, and there was like 1 bit on the left that's kind of showing what the sign is. And if you start adding zeros after the sign, you just mess up everything because it's no longer the same value. So you need to do this extension with having this in mind that this is a 2's complement encoding. So you have to actually follow the same format that you would do for a 2's complement. Again, what are the details? I specifically don't mention it because I'm assuming that you have learned this before and we don't have to go through all of those things. But I recommend to go back and quickly read your notes after this class today. Questions? Big Indian or small Indian? It's a small Indian, but we will get to that part later on as well. The question was, is RISC-V small Indian or big Indian? And I'll talk about what is small Indian and big Indian later on. Don't worry about it. It's not relevant here for now. Any question? Any other questions? Okay, but if the numbers are unsigned, then you can just forget about sign extension and 2's complement and all those things. Just add zeros and happily live your life. Okay, but unfortunately, the bad news is that immediates in RISC-V are typically signed values. So you can, there is a difference between -5 and 5. There's a difference between -10 and 10. And as a result, when you need the sign extension, you actually have to do the sign extension properly. Okay. All right. So that's it with the immediates. So immediates are these constant values that we can actually directly use in our instructions. That's a great news because, for example, if you want to add 2 numbers and you want to, for example, increment things by 2 or so on, instead of like, trying to use only registers, immediates give you an additional option. You will see it's very handy. And it's a sign value as well. So there's a difference between zeros and negatives and positives. But the biggest problem with immediates is for reasons that I said I'm going to describe later, they're not exactly 32 bits. So if you want to use it in 32-bit value, you need to figure out how should I do it. And that's the sign extension part. Okay? So the question is that if the immediates are bigger than 32 bits, then what should we do? That the answer is that it's not possible. That's we're not going to have that issue. So it's always less than 32 bits. The biggest is actually going to be 20 bits. No, the sign so the question is if the sign extension is a separate operation, it's like a specific command that we need to use. No, it's actually something that will handle by hardware. And when we are designing the hardware, we will describe that's how we do the sign extension.
Where do you talk about how zero is stored in X0?
Yeah, so that's also a great question. So the question is, how in hardware are we creating these immediates? Again, we're going to talk a little bit about it, but just think about it as each number is zeros and ones. So what I would do is all I need is creating a 0 and creating a 1, and I can just gather them together in order to create that bit for me. So for example, if I want to do the number 7, I just connect the 0 bits, 1 bit, 2 bits to the VDD, the large voltage, and the other bits to zeros, and that's how I create the immediates. At the hardware level, I will design the circuit for you, but it's just basically know that it's very easy to create 1 and very easy to create zeros, and everything else is just binary, right? So you can just add them together in order to have that immediate. Any other questions over here? You had a question?
So if I write it's 5, but I have like -1 there, is it the responsibility of the assembler to figure out the sign extension, or do I have to do this?
So the question is, if I have a negative number and wants to execute the instruction, whose responsibility is to follow that? And when we are designing the hardware, we're going to talk about how the sign extension works. So the sign extension itself is actually a piece of hardware that we're going to implement. And we're going to show you that how we follow that format and understand this is a negative number and needs to be sign extended. That's one of the challenges that we need to meet when we are designing the actual hardware. So for now, as I said, the ISA, as you can see, is this standard that both the hardware and the software needs to follow, right? So the hardware also needs to understand that we are treating this number as sign numbers. So when we are designing our hardware, we need to follow that. So we need to take care of the sign extension. We need to follow these numbers as a sign and so on. All right. So the last one is memories. So memories is actually what we know as memory. Think about it as this giant array of each line is 1 byte, and we can basically address this. So for example, if you have 256 megabytes of memory, we have that many number of lines in our memory, and then we can just assign it with numbers. So it's a memory address 1, memory address 2, memory address 3, and so on and so forth. So we can, at the software level, the nice thing is that we can access this memory individually line by line and read things from it and write things to it. As I said before, the difference between memory and register is that memory is usually in order of megabytes and gigabytes. It's huge number, but it's much slower than register. So you prefer to use register as much as you can, but if you cannot, if all the registers are occupied and so on, which we're going to discuss, then we are forced to use the memory. Also, if you want to initialize your registers, of course, the values would be stored in your memory, right? So at least one time you have to go to the memory and read these values off of your memory. And we're going to talk about the memory a lot in this course. So we're going to tell you about all these things about memory.
Does that mean there's no byte level access?
So the question is that, does that mean there is no byte access level to the memory? Yes, there's actually byte level access to the memory. So you can read them byte by byte. So we're gonna, when we are reading from the memory, we're gonna read all the 32 bits. If you just need 1 byte of that 32 bits, you just ignore the rest and access that. No, it's gonna be 1 byte of data. It's increment. I'll talk about that later on when I'm describing the memory. So don't worry about it. Okay. Any other questions?
Like you explained, if we want to access 1 byte of data, then it would include multiple.
So the question is, if you want to access only 1 byte, it will probably include multiple accesses. There is a trick that we're going to use, and one specific instruction we're going to use that only loads 1 byte. So actually, I'm going to get to it very soon. Any other questions? Okay. So I'm gonna pause here. Let's have a quick break and also see if I can figure out my tablet, and then we're gonna continue in 5 minutes. All right, let's continue. Same problem with my tablet, so I'm going to continue using this. I'm not going to use my hand to draw things, so let's see how it works. So to give you just an overview of how things work with memory and processor, as I said, I'm going to give you a lot of detail about memory later on in the course. But for now, you need to understand memory and processor as these two boxes, okay? This would be our CPU, and this will be our memory. As I said, memory, what we are assuming is that basically what it goes inside the memory is this thing called address. And what it comes out of the memory is what's called a data, okay? We are assuming that every line in our memory is 1 byte. But what the processor sees is always 4 bytes together. So we always read 4 bytes at the same time. Sometimes you only need 1 byte of these 4 bytes, and which I'm going to explain later. But for now, assume that whenever we read something from a memory, we're going to get all the 4 bytes together. Okay. But the addresses inside our memory are in bytes. So for example, if I read things from 0x. So first of all, we usually add 0x at the beginning to show the difference between addresses and normal data. So if I ask memory to give me data from 0xx, what the memory will return to me is the value in this lines here. Okay. So from line 0, line 1, line 2, and line 3 together. The reason that we are doing that again is because CPU wants to read things in 32 bits because it's much more faster for the CPU than add things together and so on. We don't do byte by byte. We just do 4 together. But inside the memory, things are stored in bytes. Okay, so memory address 0 only stores 1 byte. Memory address 1 stores another byte, and so on. So if you want to read something from the memory will package 4 of them together and send it to us, okay? And then when we are saying address is 0, we're going to read address 0, address 1, address 2, and address 3 together to make that 4 byte for us, okay? It might sound a little bit weird, but there are performance reasons for it. Okay, we want our memory for compatibility reasons to be byte addressable. So in the past, always memory has been byte addressable, and it's going to continue to be byte addressable because there are lots of programs that assume it that way. But for performance reasons, you want it to be 32-bit accessible. So that's why you package them together and send it to the processor. Okay, so consecutive addresses of memory on the processor side adds by a factor of by number of 4. So if you want to read 2 memories, the next address that you should read from is going to be 0x1 011, right? So you have to read from number 4 because you already read the first 4. So the next one you want to read is the next 4, right? So this is kind of like on the processor side we jump by 4, on the memory side we jump by 1. Okay. So this is kind of like, it might be confusing, but just keep in mind that this is the way that we're going to deal from the processor side and from the memory side.
So if you try to access memory at like address 1, for example, would it still give you 0, 1, 2, 3, or would it give you 1?
Yeah, from the CPU side, so the question is that if you want to access only, let's say, address 1, what should we do? What we do is read all, like access address either 1 or 0. And what the memory going to return to us are all the 4 bytes. But on the processor side, we're going to just throw out the other 3 that we don't want and keep the 1 that we want. Does that make sense?
The question is more like, would the 4 bytes that memory gives you start at 1, or would it start at some?
It's your choice. So the question is, should we start at 0 or should we start at 1? So it depends on what address are you sending to the memory. If your address starts at 0, then you get 0, 1, 2, 3, 3. If you send it with 1, then you get 1, 2, 3, and 4.
Right, but if you were to, let's say, try to access address 1 and then it's 0, 0, is it like indexed? So I'm just like index the second byte.
So the question is, how do we handle that in terms of programming perspective? There is a specific instruction that only reads 1 byte for you, which I'm going to describe soon. So that helps that problem. So what you would do is that if you really want just 1, you say that I'm going to read 1 byte. So I want 1 byte, and that's the address. What happens in reality is that the CPU still sends the request for address 0, 0, 0, and it still gets 4. What you will see at the software side is just only 1 byte that you want. So the hardware will take care of all those things. So what I'm saying is that on the processor side, so the question is, what is this 0x11 0x100 is, right? So this is the addresses that you should send from the processor side. From the first attempt, you say, I want to read 4 bytes, and the address, the beginning address is 0x00. What will happen is that then the memory will send you 4 bytes together. Then there is no point of saying that, oh, I also want to read 0x01 because you already have it, right? So the next time that you want to access something, you jump by a factor of by number 4. So you do 00 plus 0 plus 4, which in binary is 100. Does that make sense? No, this is what I'm showing here is a binary. Yeah. Hey, Jose. What's that? Oh, okay. No, she's after me. So this next, yeah. All right. So we send an address, we get data back. Okay. The process of reading something from the memory is usually called load. Okay. Or LD. And the process of writing something to memory is called store. Okay. Or ST. All right. So when we are saying that we are loading something from memory, it means that we put the address and we take the data out. When we are storing something to the memory, we put the address, we also provide data, and that will be stored in the memory, because the memory is not just something that we read from. We also need to write things to our memory. Okay. So this data is actually bidirectional. All right. We can take data from the memory if we are doing a load. We can write things to the memory if we are doing the store. All right. And another things that you have, yeah, question. Or the question is that for RISC, is there caching? So caching is like a macro architectural concept, which doesn't have to do with the ISA itself. So it's, I mean, ISA doesn't understand what is caching is, and we're actually going to talk about caching. What store is? So the question is, what is the store? So if you want to read something from the memory, you do load. So you put the address first, and you wait for the memory to go to that address and put the results back into your data. Okay, that's the load. The store is you put the address, you also put the data, and you write something to the memory, because the memory is also writable. It's not just something that you read from. You can also write to it. Okay. So the question is, does store do 4 byte or 1 byte? Again, to always, if you always are in doubt that what's the difference between 4 byte and 1 byte, on the CPU side, we always do everything in 4 byte. Okay, so when we are writing something, we have to provide the 32-bit. We cannot provide just 1 byte. But we can also write in 1 byte, saying that, oh, rest of it is garbage. Just take care of this byte. So the same story that we can load just 1 byte, we can just also store 1 byte. But again, in terms of what's actually happening is that 32 bits will be written to the memory. Just part of it will be written, and the part of it will be just disregarded and considered as garbage. Okay. Any other questions? All right. So the final things from this slide is the base and offset. So what is base and offset? So another way to accessing the memory is when we are accessing the memory, think about the memory again as this box with lines. We usually, in order to access memory, you can either say, oh, address XYZ, or you can also do some form of what is called a base plus some offset. Okay. So for example, if I want to address 125, of course, I can say 125. Another thing that I can do is that I'm going to say my base is, for example, 100, and I'm going to add 25 to my base. This number is called offset, and this number is base. So question is, why do we need base, and what's the deal with having a base? Think about the base as this value that, for example, we store in the register. And everything is based off that base. So for example, we have arrays, right? And if you know C and C++, you will know that basically what array does is that when you're saying the name of arrays and that bracket plus the numbers, what you're really doing is that the base of your array, let's say I have an array A and I have number 2, what really happens in hardware is that this A0 has a specific address in the memory. And what happens is that this number 2 will tell that whatever this is, just add number 2 to it. And that would be the address that I want from our processor, from my memory. Okay. So it's very, very common that we do what's called base address or base displacement addressing in memory, which means that the beginning of the address is not 0, it's somewhere else. And the offset, the number that we're going to add to that number, is from that base. And the nice thing is that if I change the base, the offset can stay the same, and we can like very quickly address things to the memory. Okay. Does that make sense? Any question about this? Say that again. You can change. So the question is that if we have the base and we want to skip some of part of the memory, what should we do, right? Is that the question? So yeah, so you can change the base. So you can, of course, access illegal parts of the memory, or you can access things that you shouldn't have accessed. And there are ways to remove that, which we're going to discuss later in the course. But generally have this, for now, what you need to understand is you can either say, oh, I want to access a specific address, which is totally fine. There's no problem with it. Or you can say that I just don't know where this is. I just know the base and I know the distance from that base, which is basically the way that we are addressing arrays. We don't know like where A2 or A3 is, but we know where A0 is. And we also know that A2 is just 2 blocks away from A0. And that's how hardware also understands. You two guys, you want to sit or do you want to stand there? Yeah. That's fine. All right. So that's any other question with addressing? Yeah, please let your fellow students sit on their chairs. Okay. All right, so let's move forward. So this is it with the operands. We have registers, we have immediates, and we have memories. And that's it with the operands. So one question before we move on to the command part is how many operands should we use and how many operands are we using in RISC-V? The question for RISC-V specifically is that at most 2. So we're not going to go beyond 2 operands in one instruction. Why? Because using more operands means occupying more space. And again, for performance reason that I'm going to describe later, we won't do that. Okay, so at most for RISC-V, we will have 2 operands. And when I'm saying at most, it means that there are instructions that only use 1 operand, and there is also instruction that doesn't use any operands. It's just a command. Once I'm describing the commands, you will understand that. But for now, just know that RISC-V specifically just only use 2. ARM, for example, there are some specific cases that ARM use 3 operands, but for RISC-V, we only use 2. So the question was that the example that I gave you with add I, x1, x2, number 5, that was 3 operands, right? So the thing is that the first one is we don't call it operand. This is like a destination. So whatever you do, you typically want to store something somewhere, right? So the operands are the 2 inputs. So in that specific case, it was x1 and 5. So for example, in this specific scenario, let me actually put it here. So add I, let's say x7, x6, and number 6, for example. So these 2 will be our operands. We call it source. And this one will be our destination, which is not an operand, is the destination. It's where we're going to store these. Again, once I describe this, the second part of what the command does, I'll go back to this and describe what is exactly each of this. It's not the same thing for all the instructions. Some of them have destination, some of them don't have. But when I'm talking about the operands, it means the inputs to that command is at most 2. Yeah. So the question is that, is this a hard rule? Yes. For RISC-V, you cannot have more than 2. Because everything is hardwired in some sense. So it's not software that you can create a new class or create a new library. In order to make the changes, you have to go all the way to the hardware and change everything. Destination.
Oh.
Yeah, sorry. I'm trying to write it with my finger, which is a little bit weird. Any other questions? Cool. Yes, something that we need to talk to people. For some reason, EDU room is not working, which I don't know why. And UCLA Wi-Fi is also always not working. All right, so we're done with the operand part. Now let's focus on the command part, okay? Again, keep in mind that we are doing everything in 32 bits. So the combination of commands and operands should fit into the 32 bits, all right? Okay, so how many commands or instruction types do we have? And similar to the operands, we have 3 different types of commands. We have what's called arithmetic or ALU operations. We have memory type operations, and we have control flow type operations. All right. So again, similar to your operands, I'm going to break this down and give you some overview of which each of these are. Okay, let's focus on the arithmetic one. So the arithmetic one is the most common one, is majority of the instructions that we do in a processor is some form of ALU or arithmetic. And what it does is simple. It takes two registers or one register and one immediate and save the results into another register, which we call destination register. So with this, the second register here, the second register here is called destination. And these two registers on top here is called source registers. Source register number 1 and source register number 2. And then if you do like the example that I gave you with add-I, you can have one register, which is your source number 1. And then you have another one is immediate. So it's not a register. Okay. So, and of course, you don't do two immediates together. That doesn't make any sense, right? Because if you want to add like 2 and 5, you can just use immediate 7, right? There's no point of doing two immediates together. Okay. So the way that we're going to have this ALU operation is we always have one register, one immediate, or two registers, and we call those operands. And then one destination register, which we're going to save the results to that destination register. All right. So here, for example, are some examples. So for example, we can have what's called a subtract instruction or add instruction, which is basically subtract and add in arithmetic. So subtract x3, x2, and x1 is, so in RISC-V, the destination register is always on the left, and the source register 1 and 2 are on the right. So what this means in mathematics is basically x3 is equal to x2 minus x1. So what this means is that. Actually, let me change the color. And then add x5, x1, and x10 means x5 is equal to x1 plus 10. Okay. So that's the meaning of these two. The leftmost one is a destination register. The other two are source register 1 and source register 2. Or if you have an immediate, there's a source register 1 and the immediate. Questions? So the question is, should the add instruction have an add-I? And the answer is yes. And I'm going to actually talk about what is the difference between add-I and add in the next slide. But yeah, that's the typo. Yeah.
So, register, does that mean each instruction for a different destination, like a different code?
So the question is that if we have the same instruction but different destination register, does it mean a different machine code? And the answer is yes. Once we actually get to the point that's saying that, okay, now we understand this instruction, what is the machine code for this instruction? We're going to actually discuss the differences between the number of registers and so on. That's something that we don't get into this lecture, but next on Thursday, I'm going to talk about the machine code.
Previous slide, you said that you do an operation on 2 registers and save the result in another register. Does that imply that RISC-V you can't like do an operation with the register and then write it back to itself?
You can do, so the question is, can you write back the destination, the results into one register? So can I have an instruction like this, basically, like having add x5, x5, and x1? And the answer is yes. The destination register doesn't need to be this exact, doesn't need to be different from any of the source. You actually, on the most extreme way, you can actually even have something like this. You can add x5 with x5, okay? And that's also totally normal. So these are completely independent from each other. Each source could be any number between 0 and 31. Each destination could be any number between 0 and 31. And they could be same or they could be different. All right. So let's move on. So here's the list of instructions that we need to care about in terms of ALUs. Okay. As I said, we are focusing on RISC-V and we are focusing on the 32 version and we are focusing on the base version. So these are not all the instructions in RISC-V, is all the instructions that are ALU type and they are in the base version. All right. And don't worry about the details, because we're gonna give you the details always. So you always have this table in front of you during the quiz, during the homework, and everything. But what is important is understanding what these values mean, what this different instruction or this commands mean. Okay, and in this table, what I'm showing is basically the keyword for that command. So for example, add I, SLTI, add, sub, and these are basically the keywords for those commands. This is the actual instruction that we're going to use. And this is kind of like, just the description of what this does. And this is kind of like the mathematical description of what this does. Okay, so let me actually go through these one by one or group by group to give you overview of what each of these mean. Why there is no subtract immediate? Actually, I'm going to get to that point, but to give you a basic idea is that subtract is similar with, like, if you want to subtract, let's say x1 and 10, this is same as doing add I x1 and minus 10, right? So there is no point of adding an x, like wasting another instruction for sub I, because you can have immediate as a sign value. Does that make sense? We can do subtract and subtract I and then just use. So the question is, why aren't we using sub and sub I and then just add instead of add and add I and subtract? Doesn't matter, right? So add I, call it sub I, doesn't matter, right? Because you just need to, it's just a contract between the software and hardware. When it says add I, it means that it has to add things. When it says sub, it means to, again, add it with a negative. So in hardware, what really happens is that it goes through a gate that invert things and then just add. So there's no notion of subtracting hardware. There's no notion of addition. And when you want to subtract things, you just add one number with the negative of the other number. Yes, so the question, so this is just for the ALU operations. I'm going to get to the memory operations afterwards. All right, so now let's get into these instructions in more detail. So first of all, you see the difference between some of the instructions that have the name I next to them and some that doesn't. So if you actually take a look, you will see that we have add and add I. We already discussed that we don't have sub and sub I, but we also have things like XOR. We have OR and OR I, for example, right? We have AND I and AND. So there is the difference between those two is that the AND version versus AND I version means that the I word stands for the immediate. So it basically says that one operand in this instruction is immediate. Okay. So if you look at the difference between add I and add, you will see that the add, what it does is takes RS1 and RS2, which are both of them are registers, add them together and store the results in RD, which is the destination register. So basically, mathematically, think about register as this array that RS1, the index for the first one, RS2 in the index for the second one. We're reading these two values and writing the results into this other array. And as I said before, RD, RS1, and RS2 could be the same, could be different, doesn't matter. It just needs to be between 0 to 31 because we only have 32 registers. Okay, the difference between add and add I, you can see that now instead of having the second RS, the RS2, we substitute that with the immediate value or the constant value. Okay, so we're basically adding the constant to the register and storing the results into the destination. Okay, so that's the difference between add I and add. And anything that you see that has the word I in front of it, it's the same story. It's just changing one of the source registers with an immediate. So the question is that does all the operands and destination needs to be registers or immediates or not memory? If it has a memory, then it becomes a memory operation, and that's the separate story that we're going to talk about. For now, everything, so ALU operation only works on registers and only on immediate. You cannot use memory when you have an ALU operation. So if you want to have a sub-I, what you would do, let's say you want to sub-I x2 with some number. Whatever you want to do with that number, just do add-I with the negative of that number. So if you want to sub-I x1 and number 20, do add-I x1 and number minus 20. Okay, the same thing. Cool. So let's move forward. Getting better at this. And this is kind of like I'm showing all the differences between add-I, sub-I. So we have add-I, XOR I, and AND-I. We have add, sub, XOR, OR, and AND. So 5 register to register, 4 immediate operations. All right. So the next one is shift operations. So SRL and SRA. So first of all, you will have SR, which means shift right, and shift right L means shift right logical. Shift right A means shift right arithmetic. What's the difference between logical and arithmetic? Again, going back to the old days that you took this CS33 course, you probably have heard about this. When we are shifting numbers to the right, for example, if I have this number like 1100, if I want to shift this by 1 byte, what will happen is that we're going to get 110, right? And I'm going to discard this 0. So, but if I want to keep this 4 bits, what should I put here? Should I put 0 or should I put 1, right? So that's the difference between arithmetic and logical. When you do logical, you don't care about the sign. You just think that this is a sequence of zeros and ones. I shift everything to the right. I replace it with 0. So I just put zeros in the end. So that's why logical means I don't care about the sign. I don't care about this number, whether it's a negative or a positive. When I'm shifting things to the right, I'm just going to add zeros to the left. When I do arithmetic, means that now this is actually a value that I'm going to add or subtract and so on and so forth. So the sign is actually important for me. So when I'm shifting to the left, I also have to care about that this is a 2's complement representation. So I should actually add, for example, a 1 here. Okay. So as you can see here, actually, you will see that this is basically saying that, oh, I'm shifting things to the right. So I'm shifting RS1 with the number that it stores in RS2 to the right. But you will see that this one says U and this one say S. U means it's unsigned and S means it's signed. So on arithmetic one, we care about the sign, and in the logical one, we don't care about the sign. And there are scenarios that you don't care about the sign. There are scenarios you do care about the sign, and that's why you have these 2 different options. Okay. And again, one thing that you will notice is that what this means is that whatever value RS2 has, I'm going to shift RS1 with that value. Okay. So it doesn't mean that if I do SRA, for example, X3, X2, and X1. So it doesn't mean that I'm going to shift right X2 with 1 bit. It says that go and see what is the value of X1. It could be 5, it could be 4, it could be 10, whatever number it is. Shift X2 with that number of bits. So if it's 10, it means that all the 10 bits should be moved to the right. If it's 5, it means that 5 bits should move to the right, and so on and so forth. And then the results has to be stored in the destination register. It could be X2, it could be X3, it could be any other number. Does that make sense? And then the difference between A and L is logical and arithmetic. Okay. All right, moving forward. So we also have shift left. So it's the difference between the R and L. And what you will notice is that the shift left is only logical. Any idea why we don't have arithmetic shift to the left? Yeah, so on the left side, we are moving things. So if I have 1 1 1 1 0 0, if I move it to the left, it's going to be 1 0 1 1, and I have to add here something. And I cannot add 1 because that changed the value. I only can add 0 here because that doesn't change the sign of this, right? So you just shift left things and you don't care about the sign. Of course, somebody might ask that, oh, if I shift this at some point, this 0 might go here, but that's on you as the programmer, right? So if you do the overflow or if you do that, that's on you. So you don't say, oh, this is a sign number, you cannot shift it to the left. That's not an issue on the hardware. Does that make sense? So we only have shift left logical and no shift left arithmetic. Okay. And then, of course, we have the immediate version of all these three. So we have SLLI, we have SRLI, and SRAI. The difference is that instead of saying that, oh, go and look what value we have in RS2 and shift it with that way, we just say that, oh, shift it like 5 bits or 2 bits or whatever. We just give the actual number, okay? All right, so then there's another category of things, which is SLT. So SLT stands for set less than. Okay, so what it does is doing two things at the same time. It does a comparison, and also it does a set. So what does it mean? Look at the actual map for it. It's easier to understand. So set less than says that compare RS1 with RS2, and when we are doing the comparison, everything is signed because everything is arithmetic. So by default, whenever we do any operation, we do it signed. Okay, so compare whatever value that you have in RS1 with RS2. The less than says set less than, which means that if RS1 is less than RS2, then write the value 1 into the destination register. Otherwise, write the value 0 to the destination register. This is just a binary value that we write into the register. So we either write just 0, 0, 0, 0 all the way 1, or we just write this value 0. Okay? And you might again ask, why do we need it? You will see that this is going to be used a lot in our instructions, because generally you want to check whether this is bigger than the other one, and based on that, make a decision. So what you would do is that you use SLT, and then you, based on the value, you're gonna, like, if the value is equal to 0, you're gonna do this. If the value is equal to 1, you're gonna do that. You basically indirectly say which one is bigger than the other. Okay, so we don't have like what's called a compare instruction, but we have a set less than instructions kind of do the same thing. Okay, and it's kind of like also implies greater than as well, because if the value is 0, it means that RS1 is bigger than RS2 or equal to RS2. There is no, so the question is that there is no flag, so this RD becomes the flag for you. So you have to use that RD as your, like, you have to read it again, and that gives you the flag that you want. How do we check for equality? Any suggestion? How do we check for equality? What's that? You raise your hand, or yeah. So you can, the easiest thing is that you can subtract and then set less than, for example, right? Okay. All right. And then there's an unsigned version of SLT, which is SLTU, which means that we're gonna just compare the positive value of these two. So if -20 and 10, if we do the unsigned version, 20 of course is bigger than 10. If we do the signed version, 10 is bigger than minus 20. So the default one is the sine version. The SLTU one, it means that I just don't care about this, the sine, just give me the whichever is bigger. Okay. And then again, we have the I version and IU version. And that's it with all the ALU instructions, right? We cover add I. Yeah, anything that we didn't cover, I don't think so. All right. So we covered everything. Yeah. You still have the question of why there is no sub-I? I'll leave it as a homework for you. Think about it, and next time if you didn't get it, I'll tell you. But again, sub-I, maybe I'll put the math here. So adding two numbers, x1 and x2, is equal to subtracting. So these two are equal to each other, right? So if you want to do some addition, you can just do the negative. Like if you want to do subtraction, just do the negative addition.
So SLTU operation,
Mm-hmm.
that take minus 20 as 20, or does that take minus 20 as a very large value?
So the question is SLTU, what does it do exactly? Yes, it takes minus 20 as 20. Yeah.
Just re-explain the difference between why we have a shift left I think I
Yeah, why don't we have the shift left arithmetic is because shifting left doesn't change the sign. So if you have 1, 1, 0, 0, and you shift it to the left, you get 1, 0, 0, and then you have a hole here. And you cannot add that hole with 1. You only have to add that with 0. Because the reason for the right shift was because the sign would have been messed up if you add 0 or 1. You have to be careful. But on the left one, there is no sign. You just use the logic one. Yeah. Again, I think would be helpful today if you go back and took a little bit, just refresh your mind on 2's complement, because that helps you with the sign part of this discussion.
So we're trying to figure out whether we're trying to use greater than using the set less than instruction.
Yeah.
Would you do that by flipping it and then also checking for equality?
Yes. So the question is, how do we create greater than? You just have to do 2 instructions basically. And the question is, why don't we have so many other instructions and just make our life easier? Because any instruction occupies some space, and you have to come up with the minimum set that satisfies the performance that you want. Okay, so of course you can have greater than, you can have equality, you can have comparison, you can all those things. But in hardware, each of these means more space in your system, and you don't want to do that. Okay. So bear with me, guys. We are almost done. So let's actually have this simple example for you. Let's see if you can actually find the final value in X3. Okay. I give you 2 minutes to figure it out. And if you need a quick look here, SRA was shift right arithmetic. So we want to shift things to the right arithmetically. So who has the answer? Let me see if anybody else. You have a question or you want to say no? Oh, okay. What's that? 11. Anybody else with any other number? 0, 4, 2. Okay, let's see. So let's start. I don't know the answer either, so let me see if we can find it out together. So this one says x1 is equal to x0 plus 3. And remember, we said that x0 is always equal to 0. So this means that our x1 after this would be equal to 3. Okay. The second one says that after this instruction, x2 will be equal to 5. And this one says add x1 and x2 to x3. So we are basically saying that we are adding 5 to 3. And we're going to get 8 here, right? So far at the end of this instruction, we have 8. Then it says that shift right arithmetic x3, x1 times. What was the value of x1? It was 3. So if you write this down, it would be in binary 8 would be 0, 1, 0, 0, 0, right? So that's the binary value of this. And this one says, and this is a positive value, right? So it has all these zeros all the way to 31. So this one says shift this 3 bits to the right. So that's first bit, that's second bit, that's third bit. So what we're going to end up with is value equal to 1. So x3 after this would be equal to 1. Who said 1? Nobody said 1. Any questions? Yeah. Here? Because these are, so the question is, what are these zeros? Think about this, that every register is 32 bits. It's not 4 bits, right? So everything on the left is all zeros. All right, so let's have one final example, and then I'll let you go afterwards, all right? Given that you did very well on, so let's do this one. So what we want to do is adding all these numbers together, 1, 6, 8, and 9. And let's actually make it a little bit simpler because we don't have much time. So let's do 1, 6, and 8, forget about 9. And then shift left y 2 to the left and 2 to the right and subtract these 2 and put it into Z. Write the assembly code for this. So you need to first do the sum of these 3 numbers. And of course, we cannot do in one go. We have to do it in multiple tries. So multiple instructions for the first part. And then, of course, the second part is also multiple instructions because you have a shift left, you have a shift right, you have a subtract. So that's probably 3 instructions. So let's see if we can do it in assembly. I'm giving you a hint here, not a hint, it's just general knowledge that x0 is equal to 0. So if you want to do sum, you probably want to initialize your accumulator with 0 first, right? Anybody done? Show of hands. Who finishes? You're not gonna try? Oh, you're done? All right. So any volunteer, what's the first thing we think we should do? So first of all, one question that you might ask yourself is, what are the registers should I use? And for now, just start from x1 and go all the way up. So that's typically the general rule of thumb. That the first variable goes into x1, the second one goes to x2, and so on and so forth. Okay, but it's totally fine if you decide I want to start from x16 or x7 or any other random number. Okay, as far as it's some number between 0 and 31, that's totally fine. And also keep in mind that you cannot use x0 as your variable because it's always hardwired to 0. Okay. So what I would do is that, let's say I want to use this sum, this y, as x1, okay? So the first thing I'm going to do is that I'm going to say x1 is equal, so like I'm going to write an assembly code. So I'm going to say add I. It's going to be tough to write it here, but I'll try. So x1, x0, and one of these numbers. So maybe number 1. So what does this do is that it's going to initialize x1 to number 1 because I know x0 is equal to 0, and that's the first thing I'm going to do. Then I'm going to keep adding numbers, right? So I'm going to do another addi, x1, x1, and number 6, because I'm accumulating. So it's important that one of the source registers should be x1. And then I'm going to repeat one more time again, x1, x1, and number 8. Okay. So at this point, I'm going to have the sum that I wanted, right? Does anybody have a question here? Okay, so the second thing is, okay, what should we do with this? This is, again, you can do, for this part, I'm going to do x1. So this is shift left. So it's going to be SLLI, x1, x1, and number 2. The second part here would be shift right, and it's going to be arithmetic because these are sign numbers. And it's going to be also SRI, and it's going to be, again, x1, x1. Oh, so by the way, we cannot use x1 here. So we actually have to use something else. So I'm going to use x2 here. So it's going to be x2. And again, here I cannot use x1 or x2. I'm going to use x3 here. So x3, x1, and 2 here. And then I'm going to just do sub, maybe x4, and then x2, and x3. Does that make sense? You cannot do 2 immediates at the same time. Yeah. And you cannot use any other values because you don't know what's the initial value of that register is. What's that? Oh, you cannot use the logic one because this is an arithmetic operation. Yeah, the default is that everything is signed.
So there's no, that's kind of.
There is no move yet, but we will talk about move too. Give me a second. Let me stop sharing and